All right, there we go. So potentially I just lost, years of work, but that's okay. We can always start from scratch. All right, why don't I start out with the question of what does conservation of momentum mean?
Momentum is conserved.
All right, we are cooking now. What does that mean?
Care to elaborate?
Or did you just lay it out for someone else to pick it up?
I'll let someone else carry it from there.
You said conservation of momentum.
He said conservation of momentum.
Okay, what was your question? Sorry?
Oh, I guess I did say it too. He said momentum is conserved. I asked what is conservation of momentum. He said momentum is conserved. And then I asked, what does that mean? So I apologize. Once again, I was trying to be a smart aleck and ended up just being a smart ass.
Are they not the same thing?
They are, so
You're not,
what Ian said is 100% correct and not particularly insightful.
you're not creating more momentum and you're not losing any momentum?
Okay, yeah. So if I have two objects in a collision and momentum is conserved, are you making the claim, Brandon, or if someone wants to pick up the mantle from Brandon, is the claim that if I have two objects that collide, that this object over here will not lose any momentum?
That was the claim, yes.
That each individual object will maintain whatever momentum it had. That. Doing the classic cleaning glasses to avoid, like Bernard in Westworld. All right, so we've established momentum is conserved and established that we don't lose any or gain any. What does it gain or lose? Let's draw pictures. Pictures are fun. Ooh, yeah. They collide. In this case, they bounce off each other.
Just their displacement's changing.
So,
If they're not losing or gaining any momentum, would the only thing be changing is their displacement? Does that have anything to do with it?
you could connect it, that's going way
Okay.
out of where I wanted to get. So what doesn't lose or gain momentum?
Objects A and B. Objects A and B.
The combination of the two doesn't lose or gain, or each individual one doesn't gain or lose?
The combined object.
Absolutely, the combined objects. All right, so if this starts out with, and let's just go ahead because I don't feel like writing the whole thing out too often, so let's define a Descartes as a kilogram meter per second, or a Newton second, depends on your mood. So if this starts out with 15 Descartes of momentum, and this starts out with negative 10 Descartes of momentum, after the collision, if this has 20 Descartes, how many does B have? Oh, give my drawing, negative 20 Descartes. How much does B have? Let's get 5.
Because we start out with 25 Descartes in the end, we need to end up with the same amount.
We don't start out with 25. How much momentum do we start out with?
5.
5.
5. We start out with 5. Alright, so my total is 5. And so my total down here has to be 5.
So 25.
Alright.
Okay.
Alright, so there's conservation momentum. How much momentum, or what was the impulse on B? And I'm also gonna ask the impulse on A. What is impulse?
Change in momentum.
Yeah, okay, so impulse is change in momentum. Or force times time, if you have that information, but we don't. So what's the change in momentum for B?
Positive 15. 35.
35,
Oh.
yeah. Final minus initial,
All
and
right.
then double negative. All right, what's the impulse on A?
Negative 35.
Okay. I've given absolutely no commentary to the mass of A or the velocity of A, mass of B, or the velocity of B before or after. No commentary, all I've talked about is just momentum. So, if I look at the change in momentum of each of them, which has a greater magnitude of change?
They're the same, aren't they?
They are the same. That's the whole idea of conservation of momentum, is that whatever one loses, the other one gains. This lost 35 units, that gained 35 units. If I come up with different numbers, the magnitude would still be the same. So on master set 8, question number 2, when I asked, there's a car and a truck that collide, which one has a greater magnitude of change? It's the same. Now, some people did recognize that momentum is conserved, and they dropped some words in their explanation. They made a comment of the occasionally change in momentum is the same, which is not true. That's positive 35, that's negative 35. These are vectors we're talking about. So the change in momentum is not the same. The change in the magnitudes are not the same, because this goes from 15 to 20. So that would be a change of 5 in the magnitudes. So be careful about the wording here. But the magnitude of the change in momentum is the same if momentum is conserved. It doesn't matter which one's bigger or which one's smaller. And on the collision problem number, I think it was 8, where you had block slides down, hits another one in a perfectly elastic collision. This hits a spring, this one bounces back up, and then I think at the last part made it perfectly inelastic, and they collide into the spring. Some people went straight to a formula for dealing with perfectly elastic collision. I mean, not a process, they just went, you look up, oh, perfectly elastic collision or completely elastic collision, here's the formula, let me plug and chug. And that's fine, except you won't have that formula on the test. And if you do the plug and chug into a formula like that and make a mistake, there is no partial credit. I want you to understand the process and be able to run the process. That's why I went through 3 different methods of solving it. So if you're gonna rely on the formula, don't make a mistake. VA final equals MA minus MB divided by MA plus MB times V initial minus, and then there's another extra term over there. And it's convoluted. And frankly, not worth memorizing if you understand the physics. All right, any questions about anything up to here? All right, it seems like we last left off where we were talking about simple harmonic motion. And we had that the position for simple harmonic motion, the position as a function of time. And this assumes x equals 0 at equilibrium. Is equal to some amplitude times either cosine or sine, depending upon which way you want to do it. Cosine of omega t plus phi. And I think last time I left the phi off, or did I throw it in at some point? We got one head shaking no. Or you can just trust Craig, or Amy, you're looking at your notes, I assume that you're checking.
It was never there.
Not there, all right. So the whole phi thing, because remember that a cosine curve starts at the peak here and then drops down. So if I start, time is equal to 0, so I start my stopwatch when I've had the thing extended the most, and then I let go. So if time is 0, when I let go, what I wrote down before hits it. Suppose I pull it back, I let go, and then you doing the timing, then you start the stopwatch after I let go. Not when I let go, but afterwards. It's not going to be starting at the peak. It's going to be starting, perhaps here. What phi is how much it has shifted. Phi is called the phase shift. And it's to deal with the fact that reality is you rarely start at the peak. And it also allows you to use sine if you want to. Because sine curve starts at the origin and moves this way. Badly drawn. It'd be more like the sine curve right there. And if you're starting at the peak, there's already a built-in shift there, so you want to be able to get the graph so that it's in the appropriate place at the appropriate time. The velocity at some time t is going to be a omega, negative a omega sine omega t plus phi if there's something there. And acceleration, probably one of these. Is negative a omega squared cosine omega t plus phi if there's one. So it seems like that's sort of where we hit near the end of class. And especially I saw Amy, she wasn't looking too far back in her notes, so I'm thinking that it was near the end. So the amplitude here from something attached to a spring and pulled back is just how far you pull it back. It's that maximum, this is the maximum displacement. Omega, the square root of the spring constant divided by the mass that's being moved. The period is, let's do it this way. Omega is also equal to 2 pi times the frequency. So the frequency would be 1 over 2 pi times omega, which makes it 1 over 2 pi times the square root of k over m. And the period is just 1 over the frequency, So the period is 2 pi over the square root of m over k. And I think it pretty much catches us up. Let me draw my radical a little bit more separate from pi. My maximum speed. Well, my amplitude, this thing sticking out front is my maximum displacement. So my maximum velocity is, that's my maximum velocity, that's my maximum acceleration right there. So doing a quick plug and chug. So I have some, let's see, got a spring with spring constant of 20 newtons per meter. Placed on frictionless horizontal surface. And placed on the frictionless. Attached 4 kilogram mass to N. Stretch spring. Said placed on frictionless horizontal surface with one end attached, or fixed, one end fixed. Stretch spring 7 meters and let go. So let's figure out all the stuff that we can figure out here, or at least a large portion of stuff that we can figure out here. So drawing the picture, just to get a visual here, I have one end fixed, which means I have one end that's not gonna move. The way I originally worded it is I just stuck it on a frictionless surface, put a mass onto it, and then stretched it. If one end were not fixed, then as I pulled on one end, the whole spring would come with me, and so I wanted to avoid that. It's not intended to be a trick question here. So I have some equilibrium position, so I attach a mass to it. I have some here, and then I pull it, stretch it out 7 meters, and I let go. So let's start out with what is the angular frequency. So first off, what symbol is used for angular frequency? That would be wavelength. And for those who weren't quite sure what Brandon mentioned lambda, this is the lambda right here. That's wavelength. As one student put it, drunk T.
Is it omega?
It is omega. A lowercase omega. Uppercase omega is the one that looks kind of like a horseshoe. All right, so first thing, finding omega. This is an indication of how rapidly this thing is going to be oscillating back and forth. The higher omega is, the shorter the period, which means it's moving faster. So, I've got a formula right over there, the square root of K over M, which is the square root of 20 newtons per meter over 7 meters, or 7 kilograms, or what mass did I put on it?
I don't think you did.
Oh, 4 kilograms, over 4 kilograms, there we go. So mathematically, the problem is what's the square root of 5? And let's actually come up with a number here, 2 point something. It's gotta be under 2.25.
2.36.
2. So what am I thinking of? Apparently I wasn't thinking too much. 2.36. Units?
Yeah, 2.23.
2.23?
Yeah.
And Amy, I guess you agreed? So we got,
Yeah,
Oh,
2.236.
so I got 3 against 1.
yeah, I misread it, my bad.
Okay. 2.23?
Yes.
All right, excellent, thank you. Units?
Radians per second.
Yes, it is. Now, just a little fun with units here, because the units actually, looking on this, the units would be newtons per meter over kilograms, which is the square root of newtons per meter kilograms, which is, well, a newton is a kilogram meter per second squared over meters kilograms, which is the square root of 1 over second squared, which is 1 over seconds. Now, the radians don't seem to appear really here, but they are there. And so you would put radians in just to communicate. We're not talking about regular frequency, we're talking